Anyway, let's get started. And to answer Mohammed's question, no, I am not in the classroom. I am home. Hashtag work from home. So yeah, what are you guys doing in my living room? So developments. So pretty much, yeah. Well, you guys are the Tuesday class, so technically I wouldn't be writing your final anyway, so. Yep. All right, I'm paying attention to what I'm wearing. Okay, cool. Hopefully everybody is here. And so yeah, it's becoming harder and harder for me to get on campus, so we'll be teaching the class out of my living room for the foreseeable future, probably for the rest of the semester, actually. And yeah, it's been a real stressful week. Pretty much the only benefit to being able to do this is now I can teach a class without having to put on pants. Kidding, I'm wearing pants. April Fools, okay. All right, let's see if things are working, because we just ran into a lot of technical issues. Okay, so I'm assuming everyone can see the notebook that just popped up. Math 212, RS2. Okay, cool. So there's a lot of stuff in here, and yeah, so I thought that all of this that I typed up over like a couple of hours got deleted. This is the lesson plan for today. So I got this this thing, for those of you who don't know, to kind of try to write directly on the notebook here. And yeah, I really suck at it still at the moment. I'm still trying to learn how to write properly with this thing. So I figure things go by a lot quicker if I just type up stuff and kind of fill in things as I go along. And yeah, even that's already hard. Like just boxing my answer, you'll probably see this later, is like really a nightmare. I really suck, which really sucks because we're going to start doing 3D things in this class pretty soon. And I was really looking forward to drawing like 3D diagrams, and like, I can't do that on this. Like, how is that going to work? Okay. Let's get back on track. We're already starting a little bit late. So let's do this. The lecture is being recorded, so whatever you're seeing on your screen right now, if you have this, the Zoom thing full screen, that's what it's going to look like. Yes. So it does have a recording feature. So we're recording right now. So let's actually just jump into it. Yeah. I was so tempted to buy a blackboard and just literally teach from a blackboard outside my home. But as you know, everyone's delivery schedule is kind of messed up. Yeah, you go to Amazon now, you order something that's non-essential, it's like there's like a 1 month to 2 month delivery waiting period. Anyway, let's get into the lecture. I actually wanted to go over some things that we did last time just to hit some things home based on some questions I've been getting in office hours and otherwise. So what I wanted to start with is talk about what we did last time. So we're right here. We're beginning. There's a delay there. Well, I'm still going to be uploading them to the same YouTube playlist. So you'll be able to access the videos the same way you always have. Like when it's recorded here, I can download it and then I upload it to YouTube. So, so you'll be able to find the videos, no worries. And I'll also, now I do recommend that you take your own notes. Some things will probably move by a little bit too quickly for you to do it in the moment, but I will be sharing a PDF version of the notes that I do in class with you guys as well, but I highly recommend you still take your own notes and do that because that'll be better for you. So last time we spoke about convergence of Taylor series, which is muy importante, very important to know about, because we get a lot out of when a Taylor series converges to the particular function that we use to generate the Taylor series. So last time we spoke about something called the remainder term, which we denoted by Rn, and we saw that if Rn approaches 0, then the series n goes from 0 to infinity of f to the nth derivative x naught evaluated x naught x minus x naught to the n over n factorial will actually converge to the original function that generated the Taylor series to begin with, provided you're on the interval of convergence. Right. So you have a convergent Taylor series, and the remainder term for that Taylor series approaches 0. It means the Taylor series approaches the function. And the big thing that we like from this is that we can then say that f of x is equal to its, to its Taylor series. Meaning the functions are one and the same. They're exactly the same thing. Whatever you can do to the function, you can do to the series. Whatever you can do to the series, you can do to the function, etc. The graph of the series would look like the graph of the function. If I plug something into the function, it's the same as plugging it into the series. They are one and the same whenever this happens. So this was very nice, and it's a very useful fact. And we looked at some uses of being able to do that. And I wanted to show you guys some animations of Taylor series, but now look at that. I literally tried to circle that phrase just now. I want to show you guys some animations, but I'm not sure if I want to risk it now. Maybe I'll do this at the end when I've gotten through everything, because the laptop's been acting up. I don't want to like open websites now and try to search for animations. Just for you to kind of see what happens as you increase the number of terms of a Taylor series and how something starts to conform to the function. It's pretty cool to actually see. But one thing I do want to emphasize is when we have a Taylor series that converges to the function, it is a very useful thing. And I wanted to show you an example of us putting this into action. So everything you know about the function, once it has a convergent Taylor series that converges to the function, everywhere that function can be used, the Taylor series can be used, including in all formulas, any identities that it shows up in, it all works. So for example, we should have memorized by now the Taylor series for 1 over 1 minus x for e to the x for sine of x and cosine of x. And so now, if I wanted to actually derive what the derivative of sine of x is, I know that we all know what it is, but just so that you can kind of see some things in action here, if I were to find the derivative of the sine of x, because I know that the sine function converges, or more specifically, this series converges to the sine function, I can literally replace sine x anywhere with that series, and it will be just as good as having sine x there. It's just another way of writing down the same thing. In the same way that writing 1 plus 1 is the same as writing 2, wherever I see 2, I can literally replace it with 1 plus 1, and no difference will happen. And so, in fact, here, because we have absolute convergence, we are allowed to switch the series and the derivative sign. And so this is x to the 2n plus 1. Now, just to make something clear, I'm going to write the 2n plus 1 factorial as 2n plus 1 times 2n factorial, which I already explained why that would be true when we looked at factorials. And so now what I can do is I just start differentiating. Now the n's are all constants. So really, the constant minus 1 to the n over 2n plus 1 times 2n factorial, these guys all stay the same, and then I just differentiate the x part. The power comes down and subtract 1 from the power. Now what's going to happen is that you'll notice that the 2n plus 1 cancels this 2n plus 1. Oh, just kind of messed up something here. Like this pointer actually works as a mouse. So if the mouse moves and the pointer is moving at the same time, it causes some sort of interference here. Let's get this mouse out of the way. Where are we? Right, so now if I simplify that, I have the series n goes from 0 to infinity of, now I'll have minus 1 to the n, x to the 2n over 2n factorial. And now you go like, oh, I know what that is. That's actually the Maclaurin series for the cosine, right? So every formula that you've ever seen the derivation of with sines and cosines, the same thing is going to work if you actually do the series. And the series is intimately connected with the properties of the function. So we know that sine of x is an odd function. It's symmetric about the origin. Notice that its power series only has odd powers. We know that cosine of x is an even function. It's symmetric about the y-axis. Notice that its power series only has even powers. The derivative of sine x, I can derive it and get that the derivative of it is cosine of x from the series version. And if you remember how you actually derive the derivative of sine of x back in Calc 1, some people might even prefer this method, because for the limit definition of the derivation, you would actually have to use the addition formula for sine, which yes, you should remember, but a lot of people didn't remember it when I was deriving it. So I just want to emphasize that once we know a Taylor series converges to a function, this is very important. The series and the function are one and the same, right? And we saw a lot of applications where we did just that. We looked at e to the I theta. We figured out it was cosine theta plus I sine theta, but just by just thinking of e as a series, which we can do at any time. So I just want you to be aware of that. Also, last time I mentioned that there were times when things could go wrong, but I don't think I gave you guys any specific examples, so I wanted to go over that as well. So because I gave my other class examples, I think I should give you guys these examples as well. So here are some things that could go wrong. So we're used to being able to differentiate any function that we see almost infinitely often. But there are problems that can arise. So for example, if you see the function f of x equals the absolute value of x cubed, it turns out that this guy, if you tried to create a Taylor series, you'd realize it has no Taylor series. Which might be strange, and you might wonder, well, why is that? Well, if I take the first, or of course, the function at 0 is 0. If I take the, or I should more specifically say Maclaurin series here, because 0 is actually the problem. The first derivative at 0, that's just going to be 3 times the absolute value of x squared, which is just 3x squared. You plug in 0, you get 0. You differentiate that, you're going to get 2 times the absolute value of x. So the second derivative evaluated at 0 is also 0. But once you go to the third derivative, it does not exist. The third derivative is undefined. Remember that absolute value of x has no derivative at 0. So this is an example of a function that we can't find a Taylor series for because it is not infinitely differentiable. And it's not a very complicated function either. And you can imagine that using this sort of construction, we can construct a function, pretty much absolute value of x to the n, that is going to be differentiable like n minus 1 times, but is not differentiable the nth time. And so that's an issue that can arise. You could have a function where you can't really kind of do this manipulation for. Here's another example. Now, to actually write down a function that will have this property is beyond our pay grade. Maybe if we're in differential equations and you saw the gamma function, I could kind of construct a function for you. But for now, a function that actually behaves like this, I wouldn't be able to write one down, but hopefully you can imagine that there would be some function that exists out there that if I were to take its nth derivative and evaluate it at 0, I might get the constant n factorial squared. Now, what that would mean its Taylor series, or again, more correctly, its Maclaurin series would look like n factorial squared x to the n over n factorial. And in which case, this is going to cancel the square, and you would find that this becomes n factorial x to the n. Now, what's peculiar about this series is that this guy diverges unless x equals 0 specifically. So this is a Taylor series for a function, but it's not a very useful Taylor series for the function because it literally works only at one point on the number line. What use is it, right? You can't really say anything if you're only at one point on the number line. For calculus to work, we need like an open interval, right? Where all points are filled in. That's how we can find derivatives, take limits, find integrals. You need some space for things to actually happen, or else your calculus is going to be useless. So this guy has a Maclaurin series. So it's not like the first example that didn't even have one. This one has a Maclaurin series, but it's completely useless. So yeah, where are we? Yeah, useless. So that's another example of something that could go wrong. You probably can't even find a Taylor series to begin with, but there are times when you can find a Taylor series and it's completely useless. Here's another example, which is also a very common example. It shows up in textbooks a lot. Let me create some space here. Oh, I'd want to move this as well. We're going to talk about the binomial theorem again in a little bit. But here's another function, a very common example. You see this in textbooks a lot. Now, this is an example of a function where you start trying to construct its Maclaurin series expanded at 0, and it seems like everything is going fine for a while, and it's actually infinitely differentiable. It turns out here that f to the n evaluated at 0 is actually going to be 0, which means that the Taylor series, or the Maclaurin series more specifically, is actually the function, is actually the series. It'll turn out to be the 0 series. Now, that will work for all x on the real line. So it is something that is technically, it's a series that works at more than one point. It works at an infinite number of points, but it's 0. Now, if you look at the function here, this f of x, it's actually not 0. Oh my God. Okay, let's try to draw a graph here. Okay, let's try something else. Let's try to ooh, not where I wanted. Okay, let's make that the x-axis. And the y-axis. And probably let's not push our luck. Okay, so what this function actually looks like. So there's an asymptote, horizontal asymptote. And the function goes like that. It's actually not supposed to go below the x-axis. It's supposed to pass through the origin. That's really bad. My God, how am I gonna do the rest of the sketching for the class? See, is it easier to draw with my mouse? Not really. So it kind of looks like that, okay? So that's what the function looks like. But of course, the zero function is not that. According to the Taylor series, the function is just a horizontal line. So that's this guy over here. So our Taylor series is the zero function, but the actual function doesn't look like that. So here's an example of a function where we can find a Maclaurin series and everything kind of works out. We can take infinite derivatives. We can evaluate them at any point on the real line, but the series converges to the zero function. This series here, where are we? This converges, of course, to some other function, say g of x, let's call it. It converges to g of x equals 0. So the original function that generated the series is not the function that the series converges to, even though the series converges. So these are just some issues that can happen when Taylor series misbehave. And the idea here is that the derivatives aren't, the remainder term doesn't actually approach 0 for this function. That was the issue here. So that's why that theorem that I mentioned last time is very useful and very important. But as we were seeing last time, when a Taylor series for a function does converge to a function, it's beautiful, it's awesome, and amazing things happen. And we can do a lot with that knowledge because we're doing calculus. It's just the power rule. It's just us writing the function as an infinite polynomial, and polynomials are easy to deal with when it comes to calculus. So those are just some things I wanted to go over. Whenever a Taylor series converges to a function, the series is the function. They're one and the same. You can derive any formula, any identity that you had with the functions before with their series versions, and a lot of times it's going to be easier. And we even looked at situations where we did limits and all that sort of stuff using Taylor series. But things can go wrong, so I just wanted you to notice that. Now, here's another thing that I wanted to go over, which I actually already did, but I think I kind of botched the explanation a little bit last time, so I actually wanted to go over it with you guys. Some students be like. So the binomial theorem. So recall this was the binomial theorem. I already spoke about that, spoke about Pascal's triangle, what this all means. This is the formula for n choose k. And normally n is considered a positive integer because in the probabilistic way of looking at the universe, that's what makes sense. You want to choose a certain amount of objects from a certain amount of other, a certain set of objects, right? However, if we relax that condition, allow n to be any value, and use the formula in the green box, and then use the Taylor series expansion of x plus y to the n, which you can find by setting f of x equals x plus y to the n, pretend your y is a constant, find all the derivatives, plug them in. You can actually, it will actually look like the original binomial theorem, except the n on top becomes an infinity, right? So this is what the binomial theorem looks like in its most general state. And if you're under the probability interpretation where your n is a positive integer, pretty much all values after the n plus first term become 0 and you don't have to worry about it. But if n wasn't an integer, for example, we tried n equals a half, that is just the square root of this sum, we can actually plug in this formula. And so if we plug in y equals 1, you can get this formula for the radical of 1 plus x. Now, what would that give? So this would give, if we started writing this out, where I still have red ink here. And let's just scroll up a little bit so you can see the formulas. Okay, so to write this out properly now, So if I wanted to find the square root of 1 plus x, this is going to be, well, I'm going to plug in k equals 0. So this is a half choose 0, x to the 0, plus a half choose 1, x to the 1, plus a half choose 2, x squared, plus a half choose 3, x cubed, plus dot, dot, dot. And how can you choose two objects from a half an object? We relax the physical interpretation of these numbers and we just use the formulas directly. So a half choose 0 is going to be 1 if I use that above formula, and a half choose 1 is going to be a half. Now, for a half choose 2, I have 2 factorial in the denominator here. And what you do is, by following that formula, it's you take a half, you subtract 1, and then you multiply. You would continue doing this. So once you have 3 factorials, it means you have 3 factors in the top. So it's a half minus 1 is minus a half minus half minus 1 is minus 3 halves. And you have 3 factors and you stop there. And then you can continue with this. So for the 4 factorial, you need 4 factors on top. So you have a half, then you subtract 1, then you subtract 1, then you subtract 1, 5 over 2, and so on, dot, dot, dot. And now when you start to actually write out what that would actually look like, if I were to expand the radical and write it as an infinite polynomial, it would look like 1 plus x over 2 minus, that would be x squared over 8 plus the 3's would cancel here. We'd have 2 to the 4th. So this is x cubed over 16 minus dot, 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 etc. So that is what this guy actually looks like as an infinite polynomial. And if you wanted to now look at what 1 over 1 plus x squared would be by this interpretation, I just plug in x squared for x in the above series. So the square root of 1 plus x squared, well, that would look like 1 plus x squared over 2 minus x to the 4th over 8 plus x to the 6th over 16. Now I want you to appreciate that this is an even function, which means it's symmetric about the y, which it should be, because the graph of this guy actually looks almost like a parabola, but not quite. It rises much slower than a parabola, so it's like a little V with a very curvy bottom. And yeah, so if you were to approximate this with 2 terms, the correct way to approximate this would be x squared over 2, right? That would be the best polynomial approximation. And that guy, well, with only two terms, that is. So this guy here would be the first 2 terms of this, and that would look like a parabola. When you zoom into 0, it's going to look very close. You can plot this at pretty much any time I do a graph. I'd probably recommend that you go to graph.tk and actually graph the things that I'm talking about, or Desmos.com or something like that. I pulled them up on the laptop, but as you can see, my laptop is not really behaving at the moment. So that would be, so first of all, we of course know how some students would be the square root of 1 plus x squared, and they would distribute the radical and write this as 1 plus x. Now, first of all, we now can appreciate that they're infinitely wrong by doing this because they have missed an infinite number of terms. That being said, it's even more wrong because that is an odd function, whereas the guy you're modeling is an even function, which means a quadratic is actually a better approximation for this than that. If they were to write 1 plus x squared over 2, they would have actually done something somewhat correct in some small interval. But yeah, just canceling and writing this as 1 plus x, total nonsense. And it's nonsense on so many levels, it's not even funny. So yeah, so I think last time it was a little bit messy here. This derivation is a lot cleaner. I think you can see it a lot nicer. Yeah, so those are just some things I wanted to cover. We've already covered these, but I wanted to go over them because it's important for you to understand. And I've been getting some questions about it. And yeah, so now let's move on to the actual new material, the lessons of today. A lot of it is going to be definitions, so a lot of it is going to be me reading to you guys these things, but we'll do some examples every now and then. Okay, so the next thing we're going to cover in this class, we're moving away from series for a while. Series are very important, but we have other stuff to do. We're going to talk about parametric curves, as they're so called. Now, we're used to seeing curves in the xy plane in what's called scalar form. So this here is called scalar form. Okay. So this is just a normal form like you're used to, like y equals x cubed. That's in scalar form, and we all know that that looks like that guy, right? And if you have x squared plus y squared equals 4, that's another scalar form that we know represents a circle. That was actually good. That's the best circle I've drawn all week on this thing. But sometimes it's convenient to think of each variable separately, right? And you want to think of the x and the y as a function in and of themselves. Like x is, I think of it as a function that has its own inner variable, and y is a function that has its own inner variable. Now, because we're in single variable calculus, you will usually think of the x and y as being functions of the same variable, which is what you see me talking about here. X is a function of t and y is a function of t. And this is surprisingly useful. And even though we haven't done parametric stuff yet, and you're going to revisit this in Calc 3, you might not have realized that you've actually been using this before to literally create an entire branch of mathematics. And it was all based on the idea of a parametric curve. So now we're going to go back into the matrix and show you what reality is really like, right? So way back in pre-calculus, right, we had the unit circle, and we had an equation for the unit circle, x squared plus y squared equals 1. And then we sort of took the idea that, well, what if we wanted to track the coordinates on the unit circle by themselves? Like, if I make this angle with the positive x-axis and it hits the circle at this point, how can I track what the x-coordinate is doing, what the y-coordinate is doing? And so what we did was we invented some functions. We invented the cosine function and the sine function. And basically these guys were to track the coordinates on the unit circle. That is essentially what sine and cosine are. So you have the unit circle. That's supposed to be a unit circle. There's got to be a better way to do this. Okay, so we have the unit circle. Oh, yes, they definitely have a circle shape. There we go. And now I should have just used the straight line shapes. Okay, so now we have the unit circle. And what we did back in pre-calculus is we looked at a coordinate on the unit circle that was connected to some angle. And we called the x-coordinate the cosine of that angle. And we called the y-coordinate the sine of that angle. What I want you to appreciate now is one way to think of this was you are saying x equals cosine of theta. In other words, you are thinking of x as a function of theta. And you're also saying that y was the sine of theta. In other words, you're thinking of y as some function by itself. And these individually were functions that do bounce up and down like that, because as you go around the circle, the points start repeating. So you get a repeating pattern and you get a periodic function, right? And just by us thinking about it that way, and then coming up with a brilliant idea of drawing a straight line here and thinking of that as a right triangle, boom, trigonometry is born. That's all trigonometry. Trigonometry is what you get by thinking of the xy plane in terms of parametric equations, where you specifically think of the x as the function cosine of theta and y as the function sine of theta. By doing that, an entire branch of mathematics is now born, right? So yeah, you've been using parametric equations for a while without even realizing it. Every time you write down a trig function, you are using parametric equations. And what you can realize then is that trig functions have their own unique behavior. And so once you start to set up parametric equations, you essentially set up a new universe that will have its own mathematical rules, its own behavior. And what we are going to do in this section is kind of talk about this in general. If we're to describe parametric equations, what does this mean in general? How can we generalize this? How do we want to think about this kind of idea in a more general sense? And you're going to realize in this class, as well as in the next class, that this idea is pretty useful. As I mentioned here, one example was trigonometry, right? So that's where we are here. Okay, so sometimes I want to think of x as a function, and sometimes I want to think of y as a function of some other variable. Think of them as functions separately. Now, when I write these two equations, x equals x of t and y equals y of t, these guys are called parametric equations. And they're called that because the variable t that you use, the new independent variable that you're using, is called a parameter. So we're writing two equations in terms of some other parameter, and it's called parametric equations. And once you take those two curves together and you give a restriction on your t values, or you just say t is allowed to be anything, you get what's called a parametric curve. Pretty much for each point, you can plug in, say, so pretty much what you're going to have is so you're on the axis. Basically what you're going to say is you're going to take t equals a and you're going to plug into the x coordinate and the y coordinate. So you're going to get a coordinate that's like x of a, y of a, and that's the initial point. Now, of course, if you plug in the b, that gives you the final point, x of b, comma, y of b, right? But you can also plug in numbers in between. So you can find x of t1, comma, y of t1. And then you can find x of t2, comma, y of t2, and so on and so forth. And pretty much what you do is you can connect these dots. And by connecting those dots, you create a curve. So this is called a parametric curve. So it's just a list of parametric points that you get from parametric equations. That is a parametric curve. So the curve describes a graph with initial point x of a, y of, that should be y of a, and x of b, y of b, which is called the terminal point or the final point. So the curve would stop at the final point here. Okay, now, in the event that we go from the scalar form, which pretty much just means we go from a situation where it's an equation that you're used to, like y equals x cubed, and I write it as a parametric form, like I think of the x and y separately. Then we say we have parameterized the curve. So for example, so if I'm looking at the curve y equals x cubed, I could create parametric equations from this. I could say let x equals t, and then let y equals t cubed. So these two equations describe the same thing as y equals x cubed, but now I list them as two separate equations. So this is called the parametrized curve, parametrized curve, or that function, right? So once I go from a situation where I have the function in scalar form to a situation where I have the function in parametric form, we say that we created a parameterization or we've parametrized the curve. I also want you to appreciate that there is no unique way to do this, right? So, where am I want you to appreciate this statement right here, that there is no unique way to actually do this. There are a couple ways that I could have written this guy, right? I could have said something like, x equals t cubed, and then just let y be the cube of that, so t to the 9th. That is also a parameterization for y equals x cubed. And the idea is we're now allowed in theory to parameterize things that would be convenient for us to use. So that's just something that I wanted you guys to be aware of. So a parameterized curve just means you go from a regular curve that it's in some y equals f of x kind of form that you're used to, and you translate it into a sets of equations where you measure each variable separately as functions. So for example, here's an example that I want to go through. So here's a parametric curve, x equals 2 minus t, y equals 3 plus 2t, and t goes from 0 to 1. I would like you to sketch this curve, okay? So how would you go about actually sketching this curve? Sorry, there are two ways I want to do this. One way is by plotting points. So you can create a table of values. So you can have a t value, an x value, and a y value. And boom, 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 right? So t goes from 0 to 1. So if your t is 0, you just plug that into the x equation. You would get x equals 2. You would get y equals 3. That's 1 point. And then you can plug in something else. So you can plug in something like t equals a half, right? Or t equals a quarter. And you can find the x coordinate for that. So it's 2 minus a quarter. That's 7 quarters. And this would be 3 plus a half, which would be 3.5, etc. Right? So you can do that. And you can keep going until you get to the last point where t equals 1, and your x would be 1, and your y would be 5. And what you can do now is you can realize that this is just going to give you a curve where you can plot these points. So you can plot the point 2, comma 3. And then you can, eventually you'll get to a point where you're at 1, comma 5. Now, of course, you're plotting points all the way in between these guys. But basically what you've realized is that you would have just constructed a straight line. And I've learned my lesson, so I'm just going to use, the line doesn't actually. Okay. Let's do this. Okay. So you would eventually construct a straight line from this point connecting that point, where you would have plotted intermediate coordinates going from one to the other, right? So when your t equals 0, you got this point. When your t equals 1, you get that point. For all intermediate values of t, you would get all the points in between, and you can actually create a straight line. Now, that's one way to do it, and that's pretty much the way that we're never ever going to do it again. I'm kind of just showing you guys that just for developmental purposes. But just like how now you don't draw graphs by plotting points, I don't expect you to draw parametric curves by plotting points. Here's a better way. One thing you want to do is you can eliminate the parameter. So this means you are actually going to go from parametric scalar form that you're used to, and draw the curve from there. So if I have x equals 2 minus t, and I have my y equals 3 plus 2t. One thing we can do is from the first equation, I can solve for t, right? So my t would be 2 minus x, and then I can plug that into the y. Y would be 3 plus 2 times 2 minus x. That would be 3 plus 4 minus 2x. And that would mean that my y is equal to 7 minus 2x, which you know is the line, right? So, and then you can just go to your axes and you can draw that line, 7 minus 2x. And of course, if you have a final point and an initial point, you'll know that this is what you are when t equals 0, and you'll know this is what you are when t equals 1, and you kind of just ignore the tails. Right, so you just ignore this part over here, and you ignore this part over here. Okay, so you'd still get the same line. You know that the y-intercept will be 7, slope is minus 2, and you'll create the same line that way. So eliminating a parameter is another method. Eventually, you will get so good at this, and of course, by the time you get to Calc 3, that is the goal, so that you would not need to do either of these methods, but you would be able to look at something like this, and you'll just know it's a line just by looking at it. Which brings me to the next, well, I'm gonna come back to that actually. Let's do another example. There's something else I want to mention here, but did I make a note of it? Yes, you probably noticed. Okay, so I'll talk about that later. So that's one way. I can sketch this. I can realize that it's a straight line, and I can figure that out plotting points, which is not the recommended method. That's the method when you're in a test and you freaked out and you forgot all the math that you know about, and so you just have to really build things from scratch again. It's not the way that I would recommend you doing it because it wastes a lot of time. Or you can do it algebraically by eliminating the parameter, get it in a form that you're used to seeing, and then sketching that. Pretty soon you'll be able to sketch from this idea directly, and that would be the hope for since Calc 2. Now, here's another example. How would you go about sketching this guy? Okay, now I've been talking for a while. Maybe someone can chime in here.
Can't you just do the same method and solve for t?
First of all, what kind of curve do you think that is? And of course here, I gave you no restriction on t, so t can be anything here. So t is anything between minus infinity and infinity.
Oh, wait, what did you say? I walked away.
Keep looking at my picture over here.
Sorry, I needed to grab my computer charger.
How would you do it? How would you solve for t? What kind of curve is it? So I know it's a curve, but what kind of curve? Can you see what kind of curve it's going to be? Well, the x is a linear and the y is a quadratic. So, oh, some people think it looks like a cubic. Well, let's see. So if I were to solve for t, I would of course do it from the x equation, so I don't have to worry about radicals. So my t would be x minus 1 all over 2. this would mean I can plug it into the y version. Y is equal to t squared. So it's x minus 1 over 2 squared. So it's a quadratic. So this is really a quarter times x minus 1 squared, which of course now I know how to actually graph that. Right? So x minus 1, it's shifted to the right by 1 unit. And then that is the quadratic right there. Now, of course, you could have plot points. You could have started with like t equals 0, and you would get x equals 1. You would get y equals 0. That would be this point here. Then you could go like with t equals 1, you would get x equals 3, and y equals 1, you get this point here. And you can go with t equals 2, and you would get x equals 5. And so you'd have this coordinate would be, what did I plug in? T equals 1. So x is 3, y is 1. Then you can plug in t equals 2, you would get x is 5, and y is 4. And you can continue to plot points like that. Now, no, the highest power of t does not determine the function. It depends on the functions that are involved. So for example, if I had that my x were something like t squared plus 1, and my y was just t squared, then that's a whole other thing. That's actually a linear function. Right? Because I could just take this t squared and plug in there. And so this parametric equation is just another way of writing, say, x equals y plus 1, which we know is actually a straight line. Right, so it depends. So you'd have to go through the method of eliminating the parameter. I know this was a quadratic because the x was the linear function, and I realized I would have solved for the t from the x and plug it into the y, and that's going to give me the square. Okay, so now, moving on to some discussion, you probably notice the following thing. And this is going to be super important for math, for physics, for engineering, for a lot of things that you are going to actually be needing a parametric way of looking at the universe for. It's actually natural to associate a direction with a parametric curve, meaning you can think of as t increasing, you're moving on the curve in a certain direction. Notice, for example, over here, when we're drawing this graph over here, when I had, when I plugged in t equals 0, it gave me this point, and that was thought of as the initial point, right? So there's already something thought of as the initial point. And then there's also something thought of as the final point, which automatically kind of tells you we're kind of traveling the curve in this direction. We're moving up, right? So we're moving from whatever point of view, you're moving up. So even when you see this curve, ordinarily, if someone just wrote y equals 7 minus 2x, it doesn't really give you the notion that there's a direction going on. However, if I write down x equals 2 minus t, y equals 3 plus 2t, and my t goes from 0 to 1, a clear direction is identified. Namely, I am moving in that direction. And in contexts where direction is important, that's important. You would much rather represent something as a parametric equation, which lends itself to a vector interpretation of the world, than to a scalar equation, which lends itself to just a magnitude interpretation of the world. So depending on the context, you might choose to represent things parametrically just because you want direction to be a part of your universe. You want there to be not only an idea of a picture, but a moving picture, like I'm going left or right on this picture, right? So that will help you talk about a parametric curve. And so that's another important thing. So you might notice that it's very natural to think of a direction. You plug in one t value, you plug in the next one, you're actually moving in a certain direction as you continue to plug in larger and larger t-values. Another thing, and that's a part of their charm, as I mentioned before, that's what's make them useful. There are patterns that would emerge. So you know that if your y is linear and your x is linear, it gives rise to a linear function. The y is linear and the y is parabolic, the x is linear, it gives a parabola. From trigonometry, you should get the intuition that if your x is a linear function of cosine and your y is a linear function of sine, this gives you a circle or an ellipse. More specifically, one that is traveled around in a counterclockwise fashion. So that brings us to the next thing. Let's talk about circles. It's a very important category of parametric equations, and it's going to be useful for 11.3, which we're eventually going to talk about. So let's talk about circles for a bit. How would you parameterize a circle? So you're given a circle, x minus h squared plus y minus k squared equals r squared. A standard way, and like I said, this is standard, it's not the only way to do it. There is no unique parameterization. That should be clear. But a standard way to parameterize a circle centered at h comma k with radius r is to use this kind of equations, this kind of parametric curve. Right? X equals r cosine theta plus h, y equals r sine theta plus k. And that is traversed counterclockwise. Once your x is a cosine and your y is a sine, it moves around the circle in a counterclockwise fashion. And if we were to switch the roles, make the y the cosine and the x the sine, that actually switches. But there are other ways to change direction as well. But why this parameterization might be something that you'd ask yourself, why do sine and cosines come up here? And again, the intuition is the same one that we used in trigonometry. So if I had x minus h all squared plus y minus k all squared, one thing I can do is I can divide both sides by r squared. And I would get things that look like, I would get the equation to look like this. So assuming your r is just some positive distance, it's a positive radius, it would look like this. So this means x minus h over r all squared plus y minus k over r all squared equals 1. And then you start to think, what do I know where the sum of two squares is equal to 1, where it's a nice function? Well, the trig functions, of course. This reminds you of the Pythagorean identity. So if I think of this guy as cosine of theta, and I think of this guy as the sine of theta, we can use the fact that I know that cosine squared plus sine squared equals 1. And so that leads us down the path of basically saying that, well, that would mean your x minus h over r is equal to cosine of theta, which if you solve for x, you would get r cosine theta plus h. And you would get that your y minus k over r, think of that as sine theta, that if you solve for y, you would get r sine theta plus k. And so that is a very standard way to parameterize a circle, right? So if you know you want to parameterize a circle of radius r, so where's my dot? For example, if I have the circle x squared plus y minus 3 equals 4. That's a circle centered at 0, 3 with radius 2. How would I write that as a parametric curve? Well, I would just set x equals 2 cosine theta, and then I would set y equals 2 sine theta plus 3, and that would be a parametric curve. And if I set something like theta goes from 0 to 2 pi, what you'll realize here is that you gain, so it's 0, 3 with radius 2. So you have a circle over here. You'll notice that as you plug in theta, you will travel around the circle in this direction. No, it's supposed to be 2, because the 4 you want to think of as r squared. So your R is 2. Yeah. So, yeah. So this immediately becomes a standard way of how we think about circles. And we're going to get back to something like this in section 11.3. But circles, a very important type of idea. And we'll start to see why it's an important idea soon. But if you want to parameterize a circle, this is the standard brain dead way of doing it. You'd only deviate from this if you're in a very peculiar situation where thinking of your circle using some other functions other than sine and cosine is going to be useful. But yeah, that's how you'd get a circle. Now, if you plug in theta equals 0, you'll start on the right side here. And as you plug in pi over 2, it'll go here. Plug in pi, it'll move over here. Plug in 3 pi over 2, it goes here. Then by 2 pi, it starts back where it started. And you'll keep going around. So you can just restrict your theta as being between 0 and 2 pi to cover the whole circle. But once I write it like this, not only is this interpreted as a circle, but it's interpreted as a circle with some sort of orientation, some sort of direction is implied by me writing this down. So not only do I get the idea of this being a circle, but there's a circle where we're traveling around it in a particular direction. And I think that's all I wanted to cover on parametric curves, just the basics, what they are. So a parametric curve is just a curve that's described when you let each coordinate be a function in and of itself. In single variable calculus, both variables are functions of the same variable. This variable is called a parameter. Therefore, these two equations are called parametric equations. Once you take a set of parametric equations together and you put a bound on the parameter, you get a parametric curve. This is just a curve in space as you're used to. However, it has the added benefit of having an implied direction associated with it. So it's a curve where, as you're plugging in t values, you can travel along this curve. You can sketch the curve by actually just plugging in coordinates and just figuring out what the x and y is for different t values and plot those points, or by eliminating the parameter. Pretty soon, you'll be able to not have to go through either of these methods, and you'll just be able to look at something and kind of know how the curve is going to behave. We did a couple examples of that, and as you can see, this one also has an implied direction. We are moving in that direction. So we're moving along this parabola in that direction. Then we can see some patterns here, and the standard way to parameterize a circle is using sines and cosines in this particular way. Something special happens when we parameterize a circle centered at the origin, where your h and k would be 0. That we'll talk about in 11.3. Okay. So do we kind of get the overall gist of everything? Because I know I'm talking really fast, but it's really just concepts and ideas and new definitions that I'm putting in here. And like I said, I'll provide these notes to you guys as PDFs afterwards. But overall, hopefully everyone's kind of following what I'm saying. But now we move on to the next section, 11.2. Now for this one, I'm going to go through this just as quickly because technically this is not in our syllabus, but I think it's a big mistake that it's not in our syllabus. It's one of those things where we're rushing. The syllabus that we're using is new, and so we're rushing to kind of fill it in appropriately. And some things were dropped out that I don't think should have been dropped out. And yeah, let's talk about derivatives. So quickly, going through this. This is a version of the chain rule. Now, we normally don't think of the chain rule in this way, but it can be written down this way. dy dx equals dy du times du dx, right? Now, algebraically, the du's can cancel and you get the dy dx, but more importantly, you kind of think of your y as a function of x, and your u is some inside function that you plug into the y. So you differentiate the y with respect to the u. That's like differentiating the outer function, leaving the inner function alone. Then you multiply by the derivative of the inner function, which is du dx. So this is one way you can express that idea. Similarly speaking, if we have parametric equations, I can apply the same idea, except instead of use the parameter t. So if I have dy dx, if I want to figure out what that looks like for parametric equations, by the chain rule, this is going to be dy dt times dt dx. And we can write that as, I probably didn't want that to be an equal sign. And that, by the way, is equal to, I can write this as dy over dt divided by dx over dt. Or you can think of this as y prime of t divided by x prime of t. So we can also do parametric equations. We can do calculus with parametric equations. And that would be the formula. That would be how we find a derivative. Take the y function, find the derivative with respect to t. Take the x function, find the derivative with respect to t, then divide them. That is your derivative of y with respect to x. So that is an important formula. Now, again, using the chain rule, we can figure out, well, not really the chain rule. We are using the chain rule, but it's kind of, it's easier to see it more algebraically, I think. So this, you would just think of it as d dx of dy dx. That's what the notation means. That's why you have a d squared y dx squared. This is Leibniz notation. I know you guys know all this from Calc 1, but we're deriving a new formula. Now this we know is d dx of, I want to separate these guys here. Now the Leibniz notation is very versatile. It allows us to do all these algebraic manipulations, which freaks some people out, but it's very convenient and very cool. Physicists and engineers love it when you do this stuff. Other people might have difficulties. What you can think of this is as d of dy dx over dt dx. And then what you do is you multiply and divide by 1 over dt, right? So 1 over a small change in t. And what you end up with then is d dt of dy dx divided by dx dt. And that is how you would find your second derivative. Right, so from the first derivative, you would find from this formula here, if you differentiate that with respect to t and then divide it again by dx dt, that actually gives you the second derivative, which is another important formula. So that's how you'd find the second derivative in parametric equations. So the first and second derivative, we can find it this way. And I'm going to do examples of these as well. Figuring out where tangent lines are horizontal and vertical are actually important. And so as far as that is concerned, this is the idea that we take along with us. So if you look at the first derivative, notice that it is dy dt over dx dt. Horizontal tangent line means that the derivative is 0, which means if it's a fraction, the numerator has to be 0. So if the numerator is 0 and the denominator is not equal to 0 at the same time, because then you have a problem, an indeterminate form, you get a horizontal tangent line. Vertical tangent lines are guys with undefined slopes. These guys would occur if the denominator is 0 and the numerator is not 0 at the same time. Then that's undefined. We know that's gibberish, and we get a vertical tangent line out of that because it shoots up to infinity. If both your dy dt and your dx dt hits 0 at the same time, then you end up with a 0 over 0 kind of indeterminate form, and you can try to use L'Hopital's rule or just take limits to figure out how the slope of the tangent line is going to behave. But these are some very basic principles that come in handy here. So you can find a first derivative using this formula. If you want to know where is the tangent line has slope 0, which is where a maximum or minimum would occur, for those of you who are wondering why I would care. All I need to do is just set dy dt equals 0, figure out where that happens. As long as dx dt is not 0 at the same time, we're good. If dx dt is 0 at the same time, use L'Hopital's rule and take the limit of this as they both approach 0. That brings us to an example. Okay, so this is talking about some calculus with parametric curves. And as I mentioned, technically this isn't in our syllabus, so I'm pretty much just going to work through these problems for you guys. And hopefully you can follow me and stop me if you have questions. So you see something like this, a pair of parametric equations. X equals t squared minus t plus 2, and my y equals t cubed minus 3t. Now, this has some curve in it, and it's not a nice curve, by the way. So this is a very complicated curve. You could solve for t using the quadratic formula in the x equation, plug that into the y, but of course you're going to have the cube of a quadratic formula. It's not going to be pretty, right? So it's a very complicated curve. But let's say I do still want to examine this curve in a calculus context. I want to talk about derivatives and second derivatives and where the tangent line is horizontal, where the tangent line vertical. What is the tangent line at a certain point, right? And so in Calc 1, we spoke about this at length, about how useful a tangent line is in approximating a function. And if the function is very complicated, as this one is, you can use tangent lines to know what's going on with the function at any point. And so that's what we're going to do here. So going through the formulas, just applying these, where's my, oh, there we are. Sometimes I lose where the pencil pointer is. A, how would you find dy dx? Well, we know there's a formula for it. This is dy dt over dx dt. So that's simply going to be 3t squared minus 3 divided by 2t minus 1. That's it. That's your derivative. That's your first derivative. It's just by following this function, that formula I gave you earlier. Now, if you look at the part B, if I wanted to find the second derivative, let's say I care about talking about the concavity of this complicated curve, I would know that that is d dt of the dy dx that I just found over dx dt. Now, of course, that's going to be the derivative of this using something like the quotient rule, bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And then I put that over the dx dt, which we already found. That's 2t minus 1. So the second derivative is going to be, well, what is this up here? This here is 12t squared minus 6t minus 6t squared plus 6. So the second derivative is in fact 6t squared minus 6t plus 6 all over 2t minus 1 cubed. That's harder than you think. Okay. So that would be how I would find the second derivative of a parametric curve. Find the first derivative, differentiate the y. No. But you would do a similar idea. So you do d cubed, dx cubed, and it'll actually be very similar to this kind of derivation. But no, you don't have to know beyond the second derivative. Find the points where the tangent line is horizontal and vertical. So, C. Let's talk about horizontal. This means your dy dt must be 0, which means that your t would be plus or minus 1, right? So if you set 3t squared minus 3 equals 0, you would get t equals plus or minus 1. Now notice these do not make dx dt equals 0, so we're good. Those are the points where we care about. So we have a horizontal tangent when t equals 1 or t equals minus 1, which means if t equals 1, our x is 2 and our y is minus 2. So this means 2 comma minus 2. At that point, we have a horizontal tangent line. So whatever the graph of this thing looks like, I don't know. But I do know at the point 2 comma minus 2 in the xy plane, this is a horizontal function. It looks like that. Well, either it can be a max or a min. We can use the second derivative to determine that, but we weren't asked. As well as minus 1. If I plug in my t equals minus 1, I would get x equals 4. And the y would be, plug in minus 1 here, that's minus 1 plus 3. Y would be 2. So at those two locations, we have a horizontal tangent line. And similarly, you can talk about the vertical tangent line. So for vertical, you would just figure out where is your dx dt equals 0. And that would mean that your t, dx dt is 2t minus 1. So that would mean your t equals a half. And so that, of course, means that your x is a half squared minus a half plus 2. And your y is, I forgot these. So it's t squared minus t plus 2, t cubed minus 3t. T cubed minus 3t. So that's going to be a quarter minus a half, which is 2 quarters, plus 2, which is 8 quarters. And so you have 7 over 4. Then this is 1/8, and this is minus 3 over 2, which is 12/8. So that's minus 11 over 8. So at this coordinate, 7 over 4, comma, minus 11 over 8, we have a vertical tangent line, meaning the curve dips vertical for that 1 second. For that 1 point, your curve goes poof. Okay. When is the slope 3? So if we look at part D, when is slope 3? So if I wanted to know for some reason, at what point in my curve are we moving at a speed of 3 in the positive direction, because there's a directional component to this. Then this just means we want to know when is dy dx equals 3. But dy dx, we already saw that was 3 squared minus 3 over 2t minus 1. I have a message here. Oh, for both of them, where do we set t equals minus 2? Oh, that's part E. We didn't actually set t equals minus 2 anywhere for part C. Yeah. So we would just solve for this equals 3, which I believe was what we got for the slope. 3t squared minus 3 over 2t minus 1. Right. So you set that equal to 3, and pretty much now you solve for t. So that's 3t squared minus 3 equals 6t minus 3. You can cancel this. No, that's plus 3. Nope, that was right. That was minus 3. So we would have here, are we? 60 minus 3. You can cancel 3's from both sides. And then you would have 3t squared minus 6t equals 0, which means you can factor out a 3t. You would get t minus 2. So you'll realize when t equals 0 and t equals 2, you have a slope of 3. Now, so the question asked when, so I will tell them the t. Oftentimes t represents time here, but you don't have to worry about that for now. T is just a parameter as far as they're concerned. If they asked where, I would actually find the x and y coordinates by plugging into the original equations here. Find the tangent line when t equals minus 2. Okay, so hold on. Curves going up and down. So E. Tangent line when t equals minus 2. And we have that's our function. So of course, this is just like Calc 1, no different from Calc 1 in terms of process. So the first thing we'd want to do is we would want to know what is the point? What's the point of all this, Jhevon? Okay, no. What is the point as in x and y location? So you take your x, it would be minus 2 squared minus a minus 2 plus 2. So that's going to be 4 plus 2 plus 2. So that's 8. The y coordinate would be minus 2 cubed minus 3 times minus 2. That's going to be minus 8 plus 6. That's minus 2. So the point is 8 comma minus 2. Then, of course, to find the tangent line, we need the slope. But the slope is just the derivative evaluated at the point. So that's d dx evaluated when t equals -2. Well, that is just 3t squared minus 3 divided by 2t minus 1 when my t equals -2. So I plug that in. That's going to be 12 minus 3 divided by -5. So that is going to be -9/5. And so my tangent line is y minus y1 equals mx minus x1. And that's the equation of the tangent line. So you can go through with parametric equations, do all the things that you remember from Calc 1 just by using these formulas. Your dy dx is dy dt over dx dt. Your second derivative is that. Horizontal when the numerator is 0 and the denominator is not 0 at the same time. It's vertical when the denominator is 0 and the numerator is not 0 at the same time. If they're both 0 at the same time, use something like L'Hopital's rule to figure out what's going on. To find the slope, you just set the formula for dy dx equals to the slope that you want. You can solve for the t values, and if need be, find the x and y coordinates. If you want to find the equation of a tangent line, you do that the same way you always do. Find the coordinate, then find the slope, plug it into the point slope form. So yeah, all that is well and good. How much time do we have here? So we're actually making good time. I mean, we started a little bit late, but I've been talking for less time than would be the normal class time. So it's actually good. So 11.2, which is everything I was talking about derivatives and calculus for parametric curves. Technically, it's not in our syllabus. So I would hold off questions on that. I would definitely recommend that you watch through this and try to actually understand it because it is something important and I don't think it should have been skipped. Well, I am going to need you guys up there. Okay, next I want to talk about an application, Arclength. So this is how to measure the length of a parametric curve. And basically you do it in pieces. So that's kind of always been the calculus way of doing things. Just dissect, cut it up into a little bit of pieces and basically use a Riemann sums idea to figure out what's going on the aggregate, right? This is going to be no different. That's what we're going to do. It's one of the essential kinds of thought process from calculus. Calculus really teaches you about two fundamental problem-solving thought processes, if you want to boil it down. It's the idea of figuring out what's going on the whole by figuring out what's going on with the little parts and kind of adding them up together. That's basically what integration teaches us. It teaches us that kind of thinking. Well, derivatives teaches us how to think of something by figuring out how to inch closer to something and figure out what's going on. So these two ideas are just general problem-solving techniques that calculus just takes and runs with them. And we get a lot of use out of just taking these simple techniques to their logical conclusion. That being said, let's talk about arc length. Here's a random curve. It's probably, and I want to think of this specifically as a parametric curve. So here is a curve. Here is a curve that's given by x of t, y of t, right? So you give me a value, let's say over here, and that was x when I evaluated at t0 and y when I evaluated at t0. Got that x and y coordinate. Then there's another point that is x when I evaluated it at t1 and y when I evaluated it at t1. Then there's another point, and this is like when I evaluated at t2, and y when I evaluated at t2. Right, so we have all these coordinates, right, which gives you the x coordinate and the y coordinate. Okay, so that's your x, let's call it x0, your x1, your x2. And this is your y0, your y1, your y2. And so here's what we basically do. I want to figure out how long is this curve. If I walked along this path, what distance would I have covered? So the first idea is to start by approximating the curve with line segments. So I connect all these points by straight lines. Now, as you can imagine, the more lines I use, you'll start to notice that if I add up all the lengths of these lines, I start getting closer and closer to the curve. So of course, the calculus point of view would be, let's use an infinite number of lines, right? So here I just draw 3 main intervals for you. For you to be able to see how it would actually work out. Maybe it would have been nicer to use 4. So you can connect that part, then connect this part, then connect that part, then connect this part, and so on and so forth. Then you measure up the length of all of these lines, you add them together, and it's an approximation for the length of the curve. Now, how do we actually turn that into some sort of theory or formula or something that's not so labor intensive? Well, you will start with just the length of each segment. So L sub I, what is the length of the ith line segment? Well, you just use the distance formula basically. So it's like x sub I you take pretty much the difference in the x coordinates, x sub I minus 1, you square it, plus you take the difference in the y coordinates, you square it, and then you take the square root. Let's try this again. And then you take the square root. Right? So this is something we know by the distance formula from pre-calc class. But then what you realize is this is just another way of saying delta x. It's the change in the x value on that interval plus the change in the y value on that interval. And now what you can do, there are many ways to think of this. Sometimes people invoke the mean value theorem here, which they can, but another way to look at it is, so you can use the fact that we can take this delta x squared and delta y squared, and we multiply by delta t over delta t, which is just a small change in the t value. And then I'm going to take the denominator and move it under the radical. So once I move that under the radical, now I have to write that as a square. So it's going to be delta x over delta t squared plus delta y over delta t squared. And delta t is out here. And so now, pretty much, let's move this down a little bit. Now what you do is to find L, which is the length, you just add up all of these Li's in a Riemann sum. Now, of course, what you know is going to happen is that's going to become an integral. My delta t on the outside is going to become a dt. And then on the inside, my delta x over delta t, well, that's just x prime of t. And my delta y over delta t, well, that's just y prime of t. So you get like this formula starting from A to B. You just add up all these line segments. Of course, adding them up in an infinite sense gives us an integral. That's what a definite integral is. It's just us adding up an infinite number of stuff. And so I get this formula over here. So that is actually the length. So this means L equals the integral from A to B of the square root of dx dt all squared plus dy dt all squared. Dt gives the length of a parametric curve, x equals x of t, y equals y of t, for t between 0 and ab. So if I want to find the length of the curve between a and b, that formula is how I would get it. So this is a very important formula. And you use this formula all over the place. There are a lot of formulas in Calc 3 that's just a generalization of this formula. And if you understand where this formula comes from, it's going to be easier for you to understand where those formulas come from. So that would be how we would find the arc length, it's called. So that's the topic that we're under, arc length. Yeah, and there are other derivations for this. Which I could show you, but I don't want to spend any more time. Otherwise, we could use mean value theorem actually, which basically is going to imply that there is a point where your delta x is going to be x prime of t times your delta t. And that's where we can get the fact that we can replace delta x over delta t by x prime, because the mean value theorem actually gives us that. So the mean value theorem says there is a point where the instantaneous rate of change is the average rate of change, which is what delta x over delta t is. So there's another way that you can get the x primes in here by invoking the mean value theorem. That's another common way to do it. But this multiplying and dividing by delta t is another way to do it. Probably the physics or engineer way to do it. A math person would probably use the mean value theorem as the way to get from this situation to that situation. Okay, that being said, we're going to just do one example. So here's another parametric curve. This one involves exponentials. And the goal here is to, I don't know what the sketch of that's going to look like, but let's say from the part where t equals 0 to the part where t equals 3, if I were to travel along this curve, what is the length that I would have traveled? This is me asking about the arc length. Find the length of this curve on the interval where t is 0 to 3. And for that, we will just plug into that formula that I just derived. And so we know that the length here is just going to be the integral from 0 to 3 of the square root of x prime squared plus y prime squared dt. This here is x prime. And this here is y prime. So what we have here. Yeah, now I just want to do this integral. I guess I would kind of multiply out these squares, e to the 2t minus, that would be 2, plus e to the minus 2t plus 4. So this is the integral from 0 to 3 of the square root of e to the 2t plus 2 plus e to the minus 2t. All right, so now you're all experts at integration. How would I integrate that? Someone help me out with this one. Starting to get dark. Okay, quickly. Well, how do I integrate that guy? Anyone? Bueller? It's the last example, last hurrah. Let's end with a bang. Any ideas? Is anybody out there? Am I all alone? Is it I Am Legend again? Any ideas?
Could you do U sub?
Stuff here.
Could you do U sub for 2t? Is my mic not working? Shit.
U sub? It's always a good first guess, right? Would that actually benefit you? Because I mean, if you had e to the u plus 2 plus e to the minus u, does that help you? If I had u instead of 2 t's in that situation, would you know what to do then? Okay, I'll give you guys a hint. Where are we? Technically, we can express the exponentials as cosine and sine, but we'll get complex numbers, which is It's not necessary here. Here's the hint. Look at this guy right here. Look at that guy right there. What's the connection between them? And by the way, probably where you should start thinking about that is this guy right here. Can you tell me another way of writing that? Right, that guy. Okay, so now you see the answer. Okay. Okay. So we did a U. This guy here is just e to the t plus e to the minus t all squared. So it's the step before U sub. Simplify. This can be simplified. I know that it can be simplified because in the above case, I realized that that part was actually e to the t minus e to the minus t all squared. That's where that part came from. It came from here. So I realized with a negative sign in the middle, it gives me this. This one had a positive sign in the middle. So it's pretty much the same kind of pattern, except now it would have a plus sign in the middle as opposed to a minus sign. Now, of course, e to the minus t plus e to the t plus e to the minus t is a positive number. Technically, when you take the square root of a square, you get the absolute value of the thing, but because it's a positive number, it's actually its own absolute value. So technically, this would be 0 to 3, absolute value of e to the t plus e to the minus t dt, but that's actually just equal to the original because the inside is positive. So that would just be integrate e to the t, we get e to the t, integrate e to the minus t, we get minus e to the minus t between 0 and 3. So that is just e cubed minus e to the minus 3. When I plug in 0, they're both the same and they eliminate each other. So that's the length, that is the distance. And that's all I wanted to talk about today. So let's do a recap. Yes, well, I know once we stop doing integrals, it'll be easy for it to slip out of your mind. We've been doing series for so long. That's why every now and then I'll ask you guys to do an integral to make sure you're keeping up with your practice. Okay, let's recap the whole lesson in a couple minutes. When the remainder term of a Taylor polynomial goes to 0, then the Taylor polynomial converges to the function that generated it. This is very good because we can think of the function as being equal to its Taylor series in the sense that we can literally swap them out one for the other at any time, and the results will be the same. For example, we derived that the derivative of sine of x is cosine of x using series when we used limits before. However, Taylor series don't always work out. There are situations where it can not work out. For example, there are functions that do not have Taylor series because you can't differentiate them infinitely often. There are functions that, even though you can differentiate them, they're too big. The Taylor series would diverge except for a single point. And there are situations in which you can find the Taylor series, but it converges to a function other than the function that generates it. So all the derivatives work out, but your remainder term does not go to 0. All these situations give you situations where the Taylor series does not represent the function that you use to create the series itself. However, when the Taylor series does represent that function, it is beautiful, and we can get so many things out of that. And a lot of last class was just us using that fact with applications. One application was the Binomial Theorem. Using a Taylor series and a generalization of this formula I could figure out how to expand things to very crazy powers, including half power, radicals. Now I know how to expand radicals and cube roots and all this good stuff if I want to expand them. The trick with those is if you're not expanding something with a positive integer power, you will always obtain an infinite number of terms. So anyone who cancels a radical across a sum, they are infinitely wrong, to put it lightly. And they will normally get something that isn't even correct a little bit when doing that. Yes, and we moved on to parametric curves. The idea is sometimes you want to think of each of your variables as functions on their own right of some other variable that we call a parameter. If you think of the x as a function of t and the y as a function of t, these are called parametric equations. You put them together and put a bound on your t, or specify that your t is unbounded, you get what's called a parametric curve. We can sketch these guys by literally just plugging in t and find the corresponding x and y values, or finding a way to eliminate the t altogether, put it back in scalar form, and draw it. This gives us not only a curve, but a notion of a direction on that curve, a direction in which the curve is being traversed. So we can talk about, oh, I'm moving on this curve to the left or to the right. That is very useful in situations where direction is important, like in physics. Did a couple examples of those, noticed some patterns, and we looked at a standard way to parameterize a circle. That's important. That's coming up in the next lecture, and why that works. Then we spoke a little bit about the calculus of parametric curves, which is actually super important, but it is not in our syllabus. This is how you would differentiate a parametric curve. Just differentiate the guy who was originally the dependent variable and divide by the guy who was originally the independent variable. But right now, you really think of t as the independent variable where these two guys are dependent on t. So this formula gets you the first derivative. The second derivative comes from this formula. And this is just us doing a lot of things that we did back in Calc 1, but with parametric equations. Things work out pretty similarly. It's just that we have to go through these formulas to get to the derivative so that we can apply it in the way that we're used to applying it. Arc length, finding the length that we are traveling along a curve. Ultimately, it comes down to this formula. You usually don't have to know the derivation, but you'd usually have to memorize this formula. And yeah, it's just an integral formula. So you pretty much plug it in. It's going to be a single integral, single variable integral, and so just integration techniques. And of course, anything is fair game here. Substitution, any of the techniques that I taught you before by parts, just simplifying, which is what this one was. It's just literally us using a little bit of algebra trickery got us to solving this integral here. And that is actually the length of the curve that I would have traveled had I moved from the point where t equals 0 to the point where t equals 3. Yeah, so that was just a recap of today's lecture. So Taylor series are important, especially when they converge to the function that generate them, and we can swap out series for functions and figure out what's going on with a function by figuring out what's going on with its series. And parametric equations, very useful. An entire branch of math that you've seen before, trigonometry, pretty much came about because of this parametric equations idea and just finding out what it would look like in this universe. This is something that you'll need to know how to do in general, and you'll go more into it in Calculus 3. But there's going to come a point later, even in this class, where I'm going to use parametric equations again and use that to talk about things and make sense of the world in a way that we couldn't make sense of it. Not only is it important for a directional point of view, but there are times when the scalar equation is just not good enough in certain contexts. Once you leave the two-dimensional sphere, how scalar equations behave changes, and it's going to be more convenient for us to use parametric equations instead. So parametric equations, very important topic. And pretty much if you're working in more than 2 dimensions, thinking of the universe in terms of parametric equations is usually far more useful than thinking of the universe in terms of scalar equations. That's something that we'll get to later, but that is it for now. Wrapping up. Not directly, no. Not in the sense that I just set things up. It's possible that you can have multivariable parametric equations. So you can have your x be a function of several variables. So it's not just t, there's like a u and a v. Think of y as a two variable function and x as a two variable function. Things of that nature happen. Parametric equations of parametric equations. Yeah, you can think of that, but the context, like we need more mathematical machinery to talk about that. Now you're sort of getting more into the realm of like tensor calculus. It's not, we probably wouldn't represent things in the way that I've been representing them if we want to go down that road. Yeah, but for now, understand parametric equations, what they're about. It's just when you take each individual, your x and y coordinate, and you think of them as individual functions of some other variable. And that allows you to think of curves in a different way, including a directional interpretation to them. So we'll stop there for now. I will post a video of this lecture with the notes. I will also post a PDF version of these notes for you guys to have. You can watch through this video, and yeah, everything here from 11.2 onwards is somewhat optional, but everything above that you really do need to know, and we'll just leave it at that. Next time we are going to cover 11.3, where we talk about something called polar coordinates, which is a whole other thing. Yeah, so I don't think you're going to see him for 2 weeks. Well, not really. So technically, I was supposed to record a lecture on Tuesday that did not happen, as you guys might have recalled, which not, I have to be at home is the short answer for that. Like I couldn't get on campus. So I'll actually record another lecture this week, but I suppose attendance is going to be optional. But you guys can watch it, and in 2 weeks' time, if you have any questions, you can let me know and we can go over it. But I will, yeah, so I'll record a lecture probably tomorrow at some point. I'll send you guys the link to it when I'm recording it so you guys can join if you happen to be available. But if not, it's okay if you just watch the video. And when I see you guys again in 2 weeks, we'll pick up from there. Practice exam, yeah, I'll get that to you over the weekend. It's been a crazy week. I wanted to get it out earlier this week, but it didn't work out. No, and it's not for me to decide, so I don't know how we're taking exams yet. Still no word from the math department about it. I know what I would like to do, but I can't actually sanction that. Which last I heard, I think it's I think they were leaning towards the thing that I wanted to do, like some sort of online proctoring service. But until I know for sure that that's sanctioned. Yeah, I still don't have anything on the actual, like a general department protocol for a test. Now, individual classes might be doing things like doing take-home tests and things of that sort, but I don't want to do that just yet. No, it's not going to be an open book final, for sure not. At least not by choice. Yeah, so normally if you go with these proctoring services, you have to, on your laptop, it will, you would do it through an app that prevents your laptop from navigating away from the browser. So it's kind of like, I don't know if any of you ever took like the GRE or one of these standard college entrance exams, but you kind of do the same thing. You can't really do an internet search while doing the exam. But yeah, the ideas are still being bounced around. I don't know for sure what is happening yet with that. But practice exams still a thing. I do intend on posting those. I'll get those out to you this week. Okay. All right. Thank you. Stay safe out there. I guess I'll see you guys in my living room another day. Until then, take care. And yeah, like I said, I'll post a video of this. You'll see my screen just like you're seeing it now on the video. And I'll post a PDF version of these notes, but I do recommend that you do write your own notes in your own notebooks. And yeah, take care. All right. Good night.